For B, we want to find orthogonal matrix P that diagonalizes A. So we first find the eigenvalue of matrix A. So consider 0 equals to determinant of lambda I minus A, and this is just the determinant of lambda minus 5, 2, 2, and lambda minus 8. So I will get lambda minus 5 times lambda minus 8, multiply is correct, minus 4, and expand this, I will get lambda square minus 13 lambda plus 40 minus 4, so I will get lambda square minus 13 lambda plus 36, and we factorize this. I think this should be okay. We see that this is actually minus 9 times minus 4, and minus 9 minus 4 is just minus 13. So yes, this is lambda minus 9, lambda minus 4, hence my lambda is equal to 9, or my lambda is equal to 4. So these are the eigenvalues. Next, we find the eigenvectors, right? So for lambda equals to 4, let's say, we find x that is not 0, such that for I minus a, x is equal to 0. So I will have what? In other words, minus 1, 2, 2, for I minus 8, so 4 minus 8, it is minus 4, xy is equal to 0, 0, and this actually means minus x plus 2y is equal to 0, 2x minus 4y equal to 0, and again we see that this equation is just the same as this equation, because you can just multiply by minus half and you will get this. So this is sort of useless. Okay. So if I let my x to be, or my y, up to you, okay, let's say I let my y to be a free parameter t, then from here I know that x is just 2y, so it is 2t. Hence my x is just t to 1, where t is real, and we can pick this as the eigenvector that we want associated with this eigenvalue. Next, for lambda equals to 9, so we do the same thing. We want to find x that is not 0, such that 9i minus a, x is equal to 0. In other words, 4, 2, 2, 1, xy is equal to 0, 0. This means 4x plus 2y is equal to 0, 2x plus y is equal to 0, and yeah, this, if I divide by 2, I will get this. So this is one of them sort of useless. And let's say I just use the second one, and I let my y to be the free variable. Then my x will be okay, maybe it is easier if I let my x to be free variable. If I let my x to be t, then my y is just minus 2t, right? So hence x is just t1 minus 2 t, and I can pick this as our eigenvector. Okay, but for this question, what we want is orthogonal matrix P that diagonalizes A. So what I need to do is I need to instead of using this as our basis, we need to normalize this. So we will have by normalizing this, I will have the set the length of this is square root 5, so 1 over square root 5 2 comma 1 comma 1 over square root 5 comma 1 comma minus 2 is orthonormal set. Okay, so we can pick this set as an orthonormal 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 basis, or okay, never mind. Okay, yeah, from question 6 we have shown that actually we do need to check whether this and this are orthogonal, because they must be orthogonal to each other. What we need to do is just to normalize this vector and normalize this vector and put it in the same set. Okay, so after we get this, we just need to write our P. So we have P is just write this column wise, 2 over square root 5. Oops, my 5 is a bit ugly. 5 and 1 over square root 5. 1 over square root 5 and minus 2 over square root 5. And by doing this, P transpose AP will become a diagonal matrix, and it is just a matrix where the diagonal entries are the eigenvalues. I made a mistake, I think, because this 2, 1 corresponds to the eigen value 4, and this 1 minus 2 corresponds to the eigenvalue 9. Okay, so it is like this. And yeah, hope it is clear.